All right. So the other day, I was thinking about a problem architecturally, and I found myself going in circles. There were many ways to solve the problem, and I found myself going into a rabbit hole of adapters, proxies, facades, even bridge patterns, finding the right way to design the code so that it's stable, reusable, flexible, all those good things. Um, so I thought I'd make a video and share some of that journey and where I landed. Before I do, though, I stumbled on this really neat quote. I know some of you have a drinking game every time I mention Robert Martin. This quote comes out of Martin's 2001 book, Agile Software Development. He goes into depth on design patterns and how they affect architecture patterns. Here's the quote. There is no such thing as enough analysis. No matter how much time you spend trying to figure out the perfect software structure, you will always find that the customer will introduce a change that violates the structure. There is no escape from this. There are no perfect structures. There are only structures that try to balance the current cost and benefits. Over time, those structures must change as the requirements of the system change. The trick to managing that change is to keep the system as simple and flexible as possible. A pattern is something that comes with both costs and benefits. So what that means to me is the reason we do architecture, especially in an agile environment, is to keep our code evolvable. We choose patterns that make certain aspects of the software more evolvable than others. You can't make all of it evolvable, and you can't, so you have to choose the axis of change. You have to choose the part of the system that is prone to change, and you're making a gamble. You anticipate the customer's changes, or you look at the multiple use cases that your system supports, and you try to design, at least in the present time, you design the system to account for those multiple use cases. As the system requirements change, as the business rules change, you are going to have to change your patterns that are implemented through the refactoring process. So, okay, speech over. So I'm going to do some drawing here. I'm using Draw.io. It's a free diagramming tool. If you're, I like to use the UML. 2.5 is the current standard. So I'm going to use a combination of component diagrams and class diagrams to illustrate my problem. So, all right, so I have a piece of software. This software is, so I have a piece of software. It could be a RESTful API or a client application or whatever, but it's a single application with a single process. And within that application, we divide the responsibilities using components. So I'll kind of move this away and detail some of those components a bit. And just to make the conversation, I'll use some really simple examples. So I have an application that is responsible for two pieces of business. One is, I'll call it a school component, and one is a work component. I call it a policy DLL. And by the way, when I say component, I mean it in the sense of the smallest unit of deployable code, which in .NET is a DLL. If you're coding in Java, it's going to be a jar. It can be an assembly or a package. But this, we call it a policy component because this is the component that contains all the core business logic of what it means to do school things. And over here is a policy component that contains all the business logic of what it means to do work-related things. So if you remember your open-close principle, we hopefully design these components to be sort of protected. So when the infrastructure around this, when the edges of the application change, and those edges could be dependency services, databases, frameworks, client UI, when those infrastructures change, we want to make sure that those core policy components remain protected. So what that means is if we have a dependency on something, we need to make sure that that dependency doesn't force a change on our policy. Rather, we want to change the dependency on behalf of the policy. So in my example, I have a need for, we'll call it settings. And this settings might be a third-party package. It's really good at getting and serving settings to any client that calls it. Its responsibility is retrieving settings, but it's a reusable package. So it provides an interface so this package has been added to our application, and it is a settings component that is responsible for getting settings. It provides an interface that allows any caller of this code to get settings. When we say a provided interface, that means it's a public interface. It's the public methods or classes available from this DLL that other components can call. Now, we could certainly write our code so that, since you know that this is inside of an application, I'll move this aside just so it's easier to draw. We can focus on the components. So we could have easily made it so that our policy components, the school component and work component, directly calls this dependency. In fact, that's not so bad. After all, this is a versioned dependency. Packages by definition are versioned and should be stable. So if there is a change to this component, it'll have a new version, which means until these policy components choose to, they don't have to upgrade. But that's still a problem, because when there's a change to this component, these components have to change. Well, that violates the open close principle. So the goal here is to design this system in a way so that regardless of what component we're using to retrieve settings, we don't violate the open close principle and cause code changes to these dependent DLLs. So how do we get around that? So the way that we protect these policy components is anything that is dependent upon, it defines a required interface. That's what these sockets are in a component diagram. So in this case, we have a required interface called I get school settings, and here's I get work settings. I purposely named these differently, not get settings, because what it means to get the school settings may and probably will be quite different than what it means to get work settings. So this interface is defined based on the needs of this policy component. Now, the thing is when you have a required interface, something must realize it. We could have written the code in a way where we invert the dependency, but this pattern won't work. And the reason it won't work is because the interface for getting the school settings and the interface for getting the work settings, well, there's no guarantee that this interface matches the provided interface, so it won't simply be able to plug in. Furthermore, these two interfaces might be completely different. Well, for one, the name is different. The method names might be different. There might be more methods on this, and there might be fewer methods on that. That would imply that maybe we could modify this package and add multiple lollipops or provided interfaces that plug in respectively. Well, that's a problem, because there could be hundreds of applications that are using this package, and that's just nonsense to change this code to accommodate every client. So how do we get around that? Well, we've talked about this before. All right, so what we've done here is we've introduced some adapters. These are pretty cheap adapters. You'll notice by the way the arrows, the dependency arrows are going down. And the reason why is in a component diagram, the arrows go in the direction at runtime, the flow of the requests for data. So the school component will make a call to the I get school settings, which is realized by a provided interface in this adapter. The request goes down. Now the adapter will hear that request and it will convert the request or wrap the request as a call to the settings component. Now the neat thing here is that, let's change this to work. So here, the adapters incur the cost of shaping the request to meet the setting component's provided interface needs of get settings. But it also realizes the requirements of the required interface provided by our two policy components. And the good thing here is that now our policy components are still protected. We don't have any code changes. That's why I'm making it green. Here it's orange, I'm indicating that code changes have happened. Blue, I'm just saying that's a package. It's a third-party package that we have no control over. Okay, so that's a great solution, but here's the problem. Let's say that this settings component is a local file. The settings are stored in a local JSON file. It's pretty straightforward. .NET Framework actually just has this built in, their configuration settings library. But let's just say we wanted a nice, easy, accessible way to get those values locally. And when I say locally, I mean in relation to the application. So for context, I'll add this box back here. So you can see the boundaries. So this application now has a dependency on this JSON file that's sort of sitting there in the local file. It has its pros and cons, but it's a common pattern. You've seen that with web config files and so on, app settings. And maybe, so what happens though if we want to replace this JSON file with a web service? When you're using draw.io, copy paste is your friend. These conventions are very important in UML. They have very specific meanings. The lollipop in this case means it's a provided interface. Because it's a web service, we're talking about the public API of the interface, probably a RESTful API in this case. But it is sure a bear to draw when you're using these drag and drop tools. Okay, so now we have this nifty new service, and maybe it's backed up by, well, we'll just say there's a database somewhere in the back. We don't even need to know about it because it's abstracted by this web service. So what we'd like to do is, for our application, we want to be able to swap this package with something else that can now call this new service, so that we're not using local configuration anymore. We can centrally configure these things. So the good news is, because we have these required interfaces up here, that honors the Liskov Substitution Principle, which says that you should be able to swap your dependency and it will have a zero effect on your core business logic, which also supports the open-close principle. So what do we do here? Well, I'll copy all of this and move this aside. These are neat. Maybe we want to use them later. Maybe in a testing environment, we want to keep these adapters handy so that we can use local configuration. But because our use case has changed, our business requirements have changed, we no longer want to use this package. We want to create a client component. We'll call it a settings service component. That's a little different than our settings component, which was really more of a local settings component. In fact, I'll even call it local, just so we can tell the difference. Now, because this is a reusable service, web service, it makes sense that we want a reusable client component as well. Now, we have a little bit of a problem. when we changed this package, we changed the interface potentially. It would be really coincidental if it was exactly the same. We can't depend on it being the same. In fact, I'll change the name of the provided interface and call it get service settings. Now, what that means is these adapters now have to change. Also, we can't use the same adapters. You saw that I copied the old adapters over. They're useful for realizing those required interfaces and specifically mapping. But adapters are meant to be cheap. They incur the cost of instability so that the things that are stable don't have to change. So in the things that we want to be stable in our system, in this case, these are our policy components and our third-party package that we can't change. Usually the adapters have very little code in it. It's just enough code to receive the request and then convert it into a call to the dependency. So here we'll create a new adapter. We'll call it school settings service adapter. Now, this is great, except what if, and this is what got me tripped up, was what if this provided interface has a dependency that this required interface up here isn't providing? So the way to visualize that is we want to get into the class diagram side of things. So over on the side, I'm going to draw what these actual provided interfaces look like. Now what I've drawn here is a little class diagram that kind of zooms in and shows you what this lollipop looks like. So the lollipop, I called it get settings. Maybe there's a method here called get setting. So a better name of this lollipop would be get setting. So this is what it was. It was really easy. The school settings adapter would say, hey, I need a setting and I need it by this name. Maybe it's, you know, street address or room number. Maybe, and it's usually by name. So it's name value pairs is what you're expecting. You would say get room number and you'd get the room number in response. And it was pretty easy, but that's because it was a local setting. However, notice that we're now making a web service call. Well, this web service needs to be authenticated, which means it needs a security token to be included. So when this package makes a call to this service, it needs to affix a token to the header, let's say. Maybe we're going to use OAuth. So this client component, the method that it needs is saying, hey, I need not only the name of the configuration, but I need the token to be passed in. So this client, so the signature is different here. The method says, pass in the string name, please, and the token. Now, certainly whoever designed this package could have implemented maybe some dependency injection pattern where they can inject a token service. Maybe through inversion of control, the main component could have injected the token service so that the signature, you're not passing the dependency in through the signature. Whatever, though, that's a design decision that was made. Rather than injecting it through the constructor, they chose to inject this dependency through the method. We can't change that fact. This is a provided package. It's very useful to us. And if you want to use it, you've got to play ball the way they designed it. And so whoever calls this code needs to be able to not only provide the name, but they need to provide the token. Well, we've got a bit of a dilemma here. Who's responsible for getting that token, that authentication token? Maybe we think of our business components, the policy components, maybe they're responsible for orchestrating it. Maybe we should refactor them so that they make a call to some token service. Let's Let's experiment with that. So what we've done here is we've added a required interface to our policy component so that as we run through the business logic, first it will call this interface to get the authentication token, it will receive it, and then it will pass it in as a parameter to the iGetSchoolSettings method. The adapter would just simply pass the name and the token down to the package. And of course, that implies that we have a component that is responsible for retrieving tokens. Okay, so we have a few problems here. The first problem is we've incurred a cost to the school component. Now we've violated the open close principle. To be able to use this required interface, well, to use this provided interface, we've said, hey, our school component will incur the cost. We'll modify this required interface to pass in that authentication token right here. And it will incur the cost of getting the school settings authentication token. Now notice I renamed this to get school settings authentication token because this is the specific token that this setting needs. There might be 14 other services that this school component needs, all with different authentication tokens. So the specific required interface here is this plugin is realizing the need specifically for the school settings authentication token. Now, I made an assumption here that we have a reusable component. Maybe it's not a package, maybe it's just a local policy component, and it's going to be reusable. Remember, we still have to refactor the work component too. We haven't even gotten there yet. So here you see that our work is multiplying. So just because we've added a token to the provided interface and we've accepted that the policy will incur that cost, we now have a code change happening here. We're going to have a code change happening up here. Of course, all of these adapters have code changes that are happening. And we've had to add this adapter here specific for this use case that we're saying is owned by this policy. Now, how could we avoid that problem? Well, it should be pretty straightforward. To protect this, remember, they defined these required interfaces for a reason, because these policy components said, I don't need to know how you get it, just get it. So let's move that away for a second. So here, we're going to go ahead and move the responsibility of getting the authentication token to our adapter. All right, so remember, when we're doing architecture and we're deciding the responsibilities of the individual components, there's going to be policies and there's going to be details. Policies are the things that need to be protected. They have the business requirements of the things that your application does. For example, we have a policy here for school that has the business logic for school things. We have a policy component for work that's the business logic for work things. Policy component for authentication token component. It contains all the business logic for dealing with and retrieving authentication tokens. And here we've got a settings service or a settings service client component, which is so reusable, we've elevated it into being a package, but it also is a policy. It can't change. So these four components must be protected and stable. And so we incur the cost of instability to these adapters. And that's okay because adapters are cheap. Now you might be thinking, gosh, this adapter looks an awful lot like a facade now because the adapter has sort of an aggregate dependency on this token component, and it's orchestrating the call to retrieve the authentication token so that it can pass it down. And that's fine. It's still an adapter from the point of view of the school component. It is realizing this required interface. And from the adapter's point of view, the provided interface is the aggregate of these two lollipops together. Now, by itself, that's fine. But remember the word facade for a moment. So remember over here, we also need to rewrite the work setting service adapter. It too needs to get the authentication token. So what we could do is the same thing. Now, I realized I kind of jumped the gun. I assumed that this thing would be a plugin, right? But if this is reusable, it can't be a plugin because you can't plug into two separate things. So what this really needs to be is just a direct call. And there wouldn't be a required interface. So this adapter incurs the cost of the direct dependency on this component. And here it's going to get a little funny with the drawing. I'm going to loop this around. Draw.io has this neat little line jump. Okay, so let's look at our application. I'll put the application boundary back in here just so it's easier to see. So we've still got our school components and our work component, and we have protected them by not violating or changing their required interface. We've swapped the settings component for a setting service component because rather than use a local setting service, we wanted to use a remote setting service, an HTTP service. The word service is loaded, so I like to put prefixes in front of all of them whenever I do, whenever I mention it. So what we've done here is we've incurred the cost of the adapters having to orchestrate the call to retrieve the authentication token that the new package requires. Now you might be thinking, wow, Steve, you're duplicating logic. Wouldn't it be cool if I could just retrieve the token and call the component twice? Or I'm doing it twice, couldn't I do it in one place? And the answer is yes, we could actually eliminate that duplicate code. And the way we would do that is we would take the part of this adapter code that is acting like a facade, and we could break it out into its own facade component. Now there's trade-offs, like I said at the beginning of this video. I'm going to go ahead and draw that, but it's going to make the system even more complicated. So we have to ask ourselves, do we want to trade the duplication of code in our adapters for complexity in the system? The answer might very well be yes. All right, so let's look at what we've built here. So we've introduced this new setting services client facade. It's very similar to the decorator pattern where we've kind of extended the functionality, but we're not so much extending the interface as we're extending kind of internal complexities. I'm calling it a facade because a facade is designed to hide complexity of underlying dependencies. Now, this one's really simple. We're only dependent on two different components. So it could be 100 components. The idea is that from the adapter's point of view, it just says, hey, I'm going to call the facade. It's going to do the thing it promises to do, and it's going to hide all that ugly complexity of orchestrating the building up of the call to this package, which will then shape the the token and put it in the authentication, put the bearer token in the header, and it'll make the request to the web service, and all that's hidden. That's what facades do. They hide complexity. So we still have an adapter that is specifically, the adapter is from the point of view of the required interface. Its job is to realize the different required interfaces. Adapters should be cheap. We really want to avoid putting complex business logic inside of them. And these two required interfaces are different, so we really want different adapters. We create this facade to put that more complex orchestration inside one reusable component so both adapters can use them. Now we don't have duplicate code inside of the adapters. Again, this facade is responsible for retrieving the authentication token and then passing it in to this provided interface that now requires the token as well as the actual setting name. It then makes the call to the HTTP service and returns it all the way up. All right, so there's no one wrong way of doing this. We could have incurred the cost or the trade-off of leaving the orchestration inside of the adapter. The trade-off would be duplicate code, also a more complex adapter. It turns out it's about the same amount of code either way. The complexity is where the boundaries are drawn. So what might help is if we see this from a class diagram point of view. Okay, I'm definitely going to speed that part of the video up. So what you have here is pretend we're not using components. Pretend our application is one single DLL. We call that a monolith. Remember, monolith isn't a bad word, it's just a design decision. So as good developers, we still practice clean code. We still use the solid principles in our code, even if it's a single DLL. Maybe we use namespaces as our boundaries instead of component boundaries. But either way, we still will have this concept of a school service class and a work service class. And we want to exercise the open close principle by closing it for modification by having it depend on required interfaces. The required interfaces allow us to support the Liskov Substitution Principle by swapping whatever implementation of these services may come along. When we swap these implementations or realizations of the required interface, then school service and work service remain untouched, and we really reduce the amount of time it takes to develop our system. So here we've illustrated that we had swapped the realization of this required interface, which stays the same and remains untouched. We've now swapped it with an adapter that has, in our design decisions, we've decided these adapters will incur the cost of sharing a dependency on this new facade. This facade also is a detail because it incurs the cost of a dependency on multiple services. Now, from the point of view of these two service classes, and when I say service this time, I'm talking about a service class. These classes provide a service. This class, the authentication token service, provides a service of getting a token, and this setting service provides a service of getting a setting. Here you can see this get settings has a provided interface. We call this a provided interface because this interface reflects the requirements of the class that realizes it. That's different than a required interface where it reflects the requirements of the client calling it. So if this adapter was the most stable, most important thing in the world, and this interface reflected that interface, this would be the provided interface of the adapter, but it's not. It is the required interface of this service. Whereas this settings service interface is the provided interface of the settings service. So here, the code, it's the same. Now, as an architect, we get to make design decisions about where do the boundaries lie. Now, as a monolith, it could just be inside of one big DLL. But we already out of the gate, we can't do that because out of the gate, we already have a boundary right here that's imposed upon us because this is a third-party DLL that we're reusing. In fact, I like to make third-party DLLs blue just so that's kind of obvious. So there's already a boundary right here. These double lines aren't official UML. It's just kind of a convention to illustrate a sketch of a boundary. We also know that there's boundary between the policies. So these, we don't want to touch these DLLs, so we put a boundary here. Now, everything else is new code. We could have made a decision to put all of these inside of one DLL. And that would be fine. This whole thing could be a sort of reusable adapter. Well, there's a problem there because, oops, and I made a mistake. It should be get work settings, school settings, right? So because these required interfaces are different, well, we've already identified that we need to split our adapters. Now, we could have created two separate facade classes like this. So this was the first design that we proposed over here. Here we said, well, the facade, the responsibility of orchestrating, we're going to just keep those shoved inside those adapters. Maybe the trade-off is we decided that the facade work is really simple. Maybe it's just 2 lines of code and we don't mind the repetition of the facade code. And that's what this would kind of look like with these boundaries. So these boundaries represent what could become components. But we decided in the last version that we want to share that facade logic. So what we do is we introduce more boundaries and we say, okay, this facade is actually going to be a reusable DLL. And by sketching out these boundaries, what you end up doing is you define the edges of what can become these components. So remember, these classes live inside these components. This lollipop in UML, whenever you see the little ball, that implies that there is a provided interface. That's what this is. So this would be a lollipop. This would be a lollipop. And you see that there's a lollipop here. You might be asking yourself, where's the interface? Well, we made a decision not to create an I setting service facade. We certainly could, especially if we're unit testing and we want that full code coverage, we could create an interface. In fact, why don't we? But even if we don't, this is the provided interface. This is the code that gets called by this code. So, or this is the code that gets called by this code. So this class is the lollipop of this component. We certainly can make a design change. Remember, anytime we have an interface on a boundary of a component, it really is a good idea to create mockable interface so that we can practice test-driven development. You might feel like, my God, we've created so many files here. All I wanted to do was get a setting. But remember, each one of these boxes contain responsibility that is owned by the components, and we want to be able to test those responsibilities independently. So we write unit tests along the boundaries of our components. So anything that is public on these component boxes, that should be testable. We should be able to mock it. So the great thing about a required interface, we can fully test our work component and its dependency on this required interface without having developed the adapter, because we write mocks in our unit tests. When those tests all pass and work code complete, congratulations, you never have to touch this component again until the business requirements change. But as long as the business requirements are stable, it is a policy that must be protected, because business is how we make the money. These details, they are changeable and they absorb the cost of instability so that we can protect these policies. So regardless of where you draw the boundaries, you're still practicing the clean code. You're still exercising the solid principles. We put them in separate components so that we can deploy or swap these at deploy time without incurring even code changes. If you did put it inside of a monolith, that's okay. You still reduce the cost of development, but you still have to deploy the whole system together, which means you have to test the whole system together. All right, so that has been a conversation about how to use adapters with facades and how we can separate the responsibilities. All right, I hope that was useful.